In this example, we're going to talk about a dart that is thrown with a velocity v0 at some angle theta, such that it hits exactly in the center of the bullseye of a dartboard, 2.38 meters away, while taking 0.449 seconds to travel that distance. As a note, we're going to cheat a little and say that the dart is a point particle, because some of this is much more complicated if we actually consider the fact that a dart looks much more like a line. I'd like to point out that if you haven't yet watched the salmon projectile video, go back and watch that first, because that video discusses in greater detail some of the concepts used to solve this problem. If we imagine that the person threw the dart such that the initial height of the dart is exactly the height of the bullseye on the target, then the dart's overall change in y position equals 0. Sometimes in this situation, it's handy to think about kinematics and refer to the equation delta y equals viy times t plus 1/2 acceleration in y times t squared. Now the next trick I'm going to use is covered with the salmon projectile video. If a projectile is released at a given height and returns to that same height, while the only vertical force acting on it is Earth's gravitational field, then I can say that my initial velocity in y is exactly the negative of my final velocity in y. So however fast it is initially traveling upward, it has to be going down at the same speed here. Note that I'm only making this claim about the y velocities. Before moving on, I want to point out that I'm approaching this problem by writing out my initial thought process. As is often the case when solving problems for which the solution is unknown, we might not need all of the information that comes to mind. To that point, the next equation that might be relevant is one that finds final velocity from initial velocity, or vfy equals viy plus g times t. Since we've already determined that final y velocity is the negative of the initial y velocity, negative viy equals viy plus gt, or negative 2 viy equals gt. Since our goal is to solve for the angle theta at which the dart was thrown, I'm going to consider v0 in terms of its components. viy is equal to v0 sine theta, and vix equals v0 cosine theta. Making a substitution then, negative 2 times v0 sine theta equals gt. Before I can solve for theta, however, I will need to substitute for my other unknown variable, v0. When considering the initial velocity in the x direction, I recall that for a projectile traveling without any forces acting in the x direction, acceleration in the x direction equals 0. If ax is 0, then vx is constant. And for objects traveling at a constant velocity, vix equals change in x over change in time. For this dart then, 2.38 meters over 0.449 seconds, or 5.3 meters per second. Remembering that vix equals v0 cosine theta, I can solve for v0 in terms of theta, 5.3 meters per second over cosine theta. Substituting this for v0 in our other equation then, gives negative 2 times 5.3 meters per second over cosine of theta times sine of theta equal to gt, or negative 10.6 meters per second times sine theta over cosine theta, which can be rewritten as tangent theta. The tangent of theta equals gt over negative 10.6 meters per second. Taking the inverse tangent of both sides leaves theta equal to the inverse tangent of the quantity gt over negative 10.6 meters per second. Plugging in negative 9.8 meters per second squared for g and 0.449 seconds for t gives us an angle theta of 22.5 degrees.